Good.
Hello, Video Land. We're studying the pendulum today. It's April the 5th, and it is a Tuesday morning. We have our note page. You can just take notes on your paper, and we draw a pendulum. It looks like that. So sketch your first pendulum, and we're going to indicate some forces that have come out to play. So draw a pendulum. And before I pull it to the side, what forces are at play right there? Can you name a force? A force MM that might exist at this point?
Gravity.
Right, the force of gravity will be downward. So the force of gravity. Can you come up with a second force? And we've studied this one. Alex? Or another force, if that was the only force, this would be going downward into the floor, or toward the floor, but it's not. It's just hanging there. Like here's one. Here's an example of a pendulum. Did you notice it?
Yeah. I was wondering what you were gonna do.
I was supposed to use it yesterday, but I figured it would last till today. So, MM found the force of the pendulum. Can you get a shot on this?
I guess the force.
The camera.
It's like, what are you talking about?
You can turn the whole tripod if you need to. Alright,
see it.
so MM found the force of gravity is downward, and this would be sitting on the floor if there was not another force. So Alex, what other force is keeping it where it is, counteracting gravity? Can you look at this thing and see where it might, what's keeping it from going down to the floor?
Force over friction?
Nope. No, there's a little there's friction until I start moving it, and friction is only due to air molecules, which we are going to negate. We're going to ignore.
Also, what about the molecular bonds between its own makeup?
Yeah, that is a force that we have. We're also ignoring.
If gravity overcame like an object sticking together by itself, then like there wouldn't be objects. It would just be a big hole.
That's right. It would just be a lot of mishmash. All right. So Brian, help us. What is the force that is keeping this where it is? Like, if gravity was the only force acting on it, it would be sitting on the floor. Tension. All right, Alex, did you hear that? Brian told us tension, and that's from the string. So, put these two forces on your picture, and that's the only two forces we're going to count. So the force of gravity is exactly equal to the tension in the string. And remember, tension is always away from the object that it is applied to. And force of gravity, of course, is downward toward the center of the earth. So now I'm going to take this object and displace it. And I'm going to put a little angle sign here, theta, to indicate that it has been displaced. And when that happens, look what happens to the force of gravity. It's still straight down, but now it creates, at this point, I'll switch colors, you're not free to always do that, but it creates a component that is the same angle as the string, and it creates a component that is pointing this way. So if I take the force of gravity, here there are no components like that because it's completely vertical. When I go over here, it's at an angle. The force of gravity is now can be broken into two components. Because this angle here is also theta, as matching this angle here, a little geometry would convince you of that. They're similar triangles, so it's going to be the angles are going to be alike. So with that, this yellow vector has a length. If this is weight, we'll call this weight, or W. It'll be weight sine theta. And this one would be weight cosine theta. I'm not going to name that one because it is weight cosine theta. But I'm not interested in the blue one. I'm interested in the yellow one. The blue one is going to counter tension. So tension over here, and this will be countering it. So the orange and the blue will equal one another, but there's nothing countering weight sine theta. So what will that force make the object do? Since there's nothing countering weight sine theta, what will it do, Zach? Do you suppose? Look at the direction it is pointing in.
It'll make it swing.
Pardon?
It'll make it swing back.
Right. That is the component that's gonna, when I pull it this way, it's gonna go that way. So, we will call that a force. And turns out, for angles that are small, when this angle is less than 20 degrees, sine theta is almost equal to theta, almost. So I'll put that little wavy equal sign. Have you ever seen that? It means approximately equal. So I can rewrite this force is weight theta. So notice I took sine theta and I boldly and liberally called it theta instead of sine theta.
Weight sine theta, which arrow is that for? Is that for the one that was going this way or the one that's going this way?
The yellow one is weight sine theta. This one?
So what's the other, the last arrow?
The blue one?
I can't tell colors.
Oh, okay. This is yellow, this is weight sine.
Yeah.
And this one's blue, this is weight cosine, but that just is countered by tension. So they cancel each other. So the one I'm interested in is this circled one, weight sine theta. It is pointing back to where this thing started from. So at less than 20 degrees, sine theta is approximately theta. So I drop the sign and call it weight theta. Now my question, is this linear? So MD, your turn. Is that a linear equation?
Yes.
It is. There's nothing squared or cubed or anything. It's degree 1. So is this linear? It is. So therefore, what we have established here is, first of all, I called this force, and noticing where it's pointing, it wants to get back to this point. This point, we can call it the equilibrium for. This point where it started is the equilibrium for the pendulum. So if there's a force trying to get back to the equilibrium, which this weight sine theta is, what do we call those kind of forces? We gave it a name for the mass spring system, MD?
Restoring?
Right, so this is a force restoring. So I put a little R there for restoring. So the restoring force is a linear relationship. And if you look back in your notes, see if this is familiar to you. When you have a restoring force that's linearly proportionate to the displacement from the equilibrium, what's that called? We had that in our notes. Can you find it? In this mod, if we have a restoring force that's linearly proportional to the displacement from the equilibrium.
Is that Haber-Cook's law?
Is that Hooke's law?
Yeah.
No. Hooke's law applies in a special case of that, but in general. You find it? You find it, Zach? It is. That was our definition for simple, or one of our remember I gave you a working one and then a fancier one? So I also gave it to you to recognize at this moment that the pendulum, when theta is less than 20 degrees, then we have simple harmonic motion. That's what SHM, you write it out, simple harmonic motion. Simple harmonic motion had a characteristic that we enjoyed with mass spring systems, because when we pulled down and let it go, do you remember that day, Alex, when you timed for us? We pulled down the spring and let it go, and you timed for us, and we found the period of 1, and then we pulled it down further, it bounced again, it was the same, we pulled it down further. So, the pendulum, also a simple harmonic motion, it ought to show the same characteristic. So let's give it a try. So Alex, will you do the honors again?
Oh, yes. Of course.
Okay.
I'm your pro timer here.
Alright. So, can you see this pendulum? It's kind of hard to see. I don't know how far 20 degrees is, so I'm not going to move it very much. And we're going to have to count the swings.
Oh, you should let it go. Timmy.
So when I say go, I'll just take it a few degrees. And when it comes back to where it starts, where I let go, call 1. And then when it comes back 2, so we get to 10, Alex.
No, stop it.
Yeah,
Well, we
so
can
help me
just lap
count.
it too.
They get lap.
If you
Hold
lapse
on.
it, then
3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop. Alright, what'd you get?
16.87. But I lapped each one, so I had each exact time for each swing.
So what was it?
So it started with 1.23, 1.86, 1.56, 1.58, 1.7.
What are you doing?
I lapped it. I lapped it.
Okay.
So you see which one every time it goes. It does it
Okay.
every different
So
time.
what do you think we got there then?
That's total time.
I guess we'll go with that. 16.8.
7 seconds.
That's pretty cool.
Yeah. So we're running laps.
Alright. So 16.87 was it? What was it?
Yeah.
Alright, so 16.87. So we divide that by 10. We get, say, 1.687, which we round to 1.7. Alright, I'm going to try to pull it a little further this time. So we are expecting the same thing if it's simple harmonic motion.
Oh, so are we starting?
Ready? I'll do the same. I'll go 3, 2, 1, start. Is that more than 20 degrees? 20's not very far.
I think it's
I think
fine.
20's hold it.
Ready? 3, 2, 1, go. 1, 2. Is that swinging more? 3, 4. Has that got a bigger angle? 6, 7, 8, 9, 10. 17 point what?
2.7.
That's not too bad. I noticed that on both of mine they were swinging a little wobbly, so if we divide that by 10, oh yeah, that's cool. 1.7. Alright, so simple harmonic motion, that means the distance we pulled it from equilibrium, which is now our amplitude, is the period is independent of the amplitude. So write that as, we wrote that before for this mass spring period. That's how long it took for it to go up and back. Period, independent. Independent of amplitude. Alright. Just like it didn't matter for the mass spring, it didn't matter for the pendulum, how far we pulled it. As long as we stay within 20 degrees. So that doesn't give us a lot of degrees, but that's where it works. Alright, so that's the basic theory of the pendulum. Let me give you the formula, which you've been waiting for. The formula for the period of a pendulum, so I'll put period of a pendulum. Here we had period of a mass spring system, and do you recall it was 2 pi times what was under the square root for the mass spring? We did problems a couple days ago on those, do you recall? M over R, it's M